Morning, everybody. A lot of people have observed this difference between regular Cartesian transformations and parametric transformations. In particular, in the horizontal axis, if I've got a Cartesian equation where I'm shifting, if I'm replacing x by x minus 2, that corresponds to a right shift, which is backwards from what you may expect. However, if we have a parametrically defined equation where x is a function of time, and you replace x with x minus 2. In this case, it's a left shift. So why the difference? So here's an example of an unshifted parent graph in a transformation that's Cartesian. So we've got the outputs are the y-coordinates, and they're functions of the inputs, which are the x-coordinates. And that's all familiar. So what I want to focus on here is, why does replacing x with x minus 2 actually mean it's a right shift instead of a left shift? Because I think that's the kind of main confusing part. So when you replace x with x minus 2 on the inside, that's like a composition of functions. What we're saying is, whatever the input x is, first let's subtract 2 before we ever send it through the x squared function. So whatever the input is, we do something to it, and then that gives us a new input that we then square to figure out what the output is. So if we want to know how does this shift the overall parabola, we could think about a key value like the vertex here at 0, 0. And we might ask, where does that shift to? So if you're thinking about it numerically, the question is, what input could you give here where that's going to end up as an output of 0? Because I know that if I send 0 through the x squared function, that's what's going to give me my y value of 0. So it's sort of like you have to solve backwards. You have to think about, what could I put here that would give me a 0 out so that I can get what would be the same as my old vertex. Clearly, whatever I put here, I'm going to be subtracting 2 from it to go this way. So if I want to end up with 0, and I think backwards, it must be that this value has to start out at 2. So what that means is, in the old coordinate system, the x values are 0, 1, 2, 3. And I'm asking for this new function. For the new function, the inputs are here. This is the x and that's the y. And all this in the middle is just stuff that gets us from the x to the y. So in the new coordinate system, I want to say, what x values here corresponds to the old x values. So if this used to be the vertex, I want to know what's the new x value that corresponds to the vertex, and I see that it's 2. And if I want to know what point is 1 to the right of the vertex, I can think about it backwards again. I know that this maps to 1, so what value could I put here that would give me 1? And the answer is 3. So if this is the original graph, the new graph has a new set of input x values that map to the same old set of output y values. And by thinking about solving backwards for which inputs will map to the old inputs, that gives us the transformation. And so let me now, in pink, graph the new set of inputs as they would appear in the old graph. So let's imagine that the x-axis in black here has disappeared. So I'm removing all of these values. So I know that when my input is x equals 2, that corresponds to the old x value of 0. So this old x value of 0 is now 2, because 2 behaves like it used to be 0. And same thing for 3. 3 behaves like it used to be 1. And 4 behaves like it used to be 2, and so on. Let's just fill in the rest. So you can see the x minus 2 happening from pink to black here. 5 minus 2 is 3, 4 minus 2 is 2, 3 minus 2 is 1. But if you look at the transformation that's happened, here's where 0 is now. So if I draw the axis there, now you'll notice that it looks like, if this is where the axis is, the vertex that used to be at 0, 0 has shifted right by 2. So the reason why it seems backwards is because we were always asking the question, how do you undo the effect that this input is having? as you go from the old input to the new input. So we want to ask what new inputs correspond to the old ones. And so you have to think backwards. You have to undo the operation. And so that's why it has the reverse effect. A different way of thinking about why it has the reverse effect is you're applying a transformation to the x-axis, but you're applying it before you ever put down the points of your graph. So think about it this way. Imagine if I place the points for my quadratic function first and then change all of the x-coordinates, that would shift it left. But the point here is you can't place the points until after you've gotten the y values out of the function that you're trying to graph. And so by replacing x with x minus 2, it's like we're shifting the x values before we ever place the points down. And that's what the pink axis is. I've shifted the pink axis left by 2, and you can see that that kind of makes sense for x minus 2. It's shifted left by 2. But I shifted it left before placing my points. So the points still get placed where they would have gotten placed before. It's just that I've shifted my axis before that ever happened. By the way, this thinking is going to be really important later on once you have two different horizontal transformations. So you see something that looks like scaling and something that looks like shifting, but what effect does that have on the actual root x graph? Is it scaling first and shifting second, or the other way around? You can think about it in the same way. You can think, all right, if I plug in an x value, what I'm doing to it on the inside is I'm multiplying by 2 and then adding 5. So if I want to end up with 0, what x value acts like the old x value at 0? And the answer is you can reverse both processes. So it's like solving for when this expression equals 0 on the inside, which is the same as finding the inverse function. So I'll subtract 5, so that's negative 5, and here I'll divide by 2, so that means negative 5 halves is the point that acts like the old 0. And so that corresponds to two transformations. So that kind of thinking is going to happen later in the year. Okay, so the last part of the story is easy. We decided that this corresponds to a right shift because you're subtracting 2 from all the x values before you actually draw the function. And that's like shifting your axes to a new location before you draw your function at the old location. So an axis shifting to the left by 2 is going to leave the point that used to be at 0 at negative 2, and it's going to mean that your old function looks like it got shifted to the right. So what about the parametric one? The parametric one is easy because the negative 2 is on the outside, and what that means is for different times, you've already found your x-coordinates. So by subtracting 2 on the outside, it means that you're taking your x-coordinates and you are literally changing the value of your x-coordinates because they've already been found. And so that example is more like the one that I had before, where you place your x-coordinates at different times, but then you take each x-coordinate and you subtract by 2. And so that really does correspond to a left shift. Okay, I hope that was helpful.